All right, welcome everyone. We're going to get started today. So we're going to continue talking about area under the curve and how it relates to definite integrals. But before we get started, I want to remind everyone for the follow-up exam next week. So we have some people in recitation today. They'll be doing their exam 6. But for next week, we have our follow-up exam, which is going to cover everything from exam 1 all the way down to exam 6. And so we've scheduled it for Thursday at 6:30. So just double check, make sure you can take it at that time. If you can't, send me an email with a screenshot of your class schedule from your Hub Student Center, and just try to get that to me. If you do have a conflict, send me that email by tomorrow so we can make arrangements. Okay, so let's continue talking about definite integrals and how it relates to the area under the curve. And we're going to look at example 2 here, where we're given a piecewise function and we're going to find the area under the graph from a equals 0 to b equals 4. So we're going to see how to handle these piecewise functions. So that's the first thing we just want to note here is we have to be a little careful when we deal with piecewise functions, because the integration, we're going to end up having to split up our integration. So if we look at this piecewise function, we see that the different pieces of our function happen kind of get split up at x equals 2. So what we see is that if x is less than or equal to 2, our piecewise function is defined as x. And if x is greater than 2, sort of the other piece of our function here, if x is greater than 2, well then our function is defined as the constant function 2. So piecewise functions, there's different pieces involved. And what we see here is that really where the pieces get split up is when x is equal to 2. So we're just going to note that first of all. This is a piecewise function that splits into its different pieces at x equals 2. All right, so what are we going to do in this problem? We want to find the area under the graph of this function f of x from a to b, where a is equal to 0 and b is equal to 4. So graphically what we're attempting to do here is we're trying to figure out the area starting at a equals 0 and going until b equals 4. We're trying to find the area under this curve. So let's just shade in the region of the region that we're going to calculate the area of. And we just note a few things. When we look at this graph, f of x is on or above the x-axis. For the interval 0 to 4. Eventually, if we had more of our graph there, kind of the negative x values, we do see a little bit of the graph there goes below the x-axis, but just in that interval from 0 to 4, that's all we're concerned about. So in that interval 0 to 4, our function touches the x-axis at one spot, but for the most part it's above the x-axis. And our function is continuous. So there's no jumps or breaks in this graph. So to calculate the area then, just becomes just an integration problem. We just need to integrate our function f of x from 0 to 4. And we can just integrate just our function f of x because it's above the x-axis. So how we integrate a piecewise function is we really need to split up our integration then wherever our piecewise function splits up. So what we're going to do is we're going to look at the integral from 0 to 2 of f of x. And then we'll look at the integral from 2 to 4 of f of x. And so really what we're doing here is where our function splits at x equals 2, we also then have to split up the integration. And we know we can do that because that's one of our definite integral properties. So as long as kind of all the pieces join together, we can use the property of definite integrals to split up the integration. And then we're going to calculate each of these separately. All right, so let's actually fill in then what our function is for each of those pieces. So if we're doing the integral from 0 to 2, which piece of our function should we use? Well, if we're doing the integral between 0 and 2, really what's happening here is x is less than or equal to 2. So think of the limits of integration as sort of being the endpoints of the interval we're considering. So we're only in between 0 and 2. And so the piece of our function that describes that is right here, the first piece. So we're going to fill in x as our function because that's how this piece is defined. It's defined as x. Then we'll go to the integral from 2 to 4. Now here, x is between 2 and 4. So here really x is behaving, we're going to look at the piece where x is greater than 2. And so when we go to our definition of our function, we find the piece where x is greater than 2, and we look up to see how our function is actually defined there. And we see that it's just a constant function. So in this case, 2. So that's why we really had to split this integral up, is because those different pieces, we're going to get different integrals that we have to calculate. All right, so from here we can do, now it's just regular integration. So get the antiderivative and then evaluate. So what's the antiderivative of x? It's 1/2 x squared. And we'll evaluate that from x equals 0 to x equals 2. Then if we do the other integral, the integral of a constant is, in this case, would be 2x. And we evaluate that from 2 to 4. And then we just plug in. So we go through and do our evaluation. So when we plug into that first one, we get 1/2 times 2 squared. And then when we plug in 0, we get 0. I'll write it, but we don't normally have to write that. We'd get 1/2 2 squared minus 0. Then we go to our other evaluation. We plug the top number in first. We get 2 times 4, which is 8. Then we plug in the lower number, which is 2, and we plug that in. We get 2 times 2, which is 4. And then just clean this up. And we end up with 6. So that's the area of that region using definite integrals. Now, if we're looking at that region, it's something we can also just calculate with basic geometry. So some of the problems that we're going to look at, you might be able to just use basic geometry to calculate the area instead. So if we look at this, and that's what we're going to do, we could just use geometry for this one. Because the region is, if we look at this, we can kind of break it apart into easy to calculate areas. So first we could kind of break this one. That's just a triangle. Calculate the area of the triangle. And then this here is a rectangle. That's actually a square. So we could just calculate that, the area of that rectangle there, and then just add the two areas together. So area would be the area of the triangle. And then we could add to that the area of the rectangle. So what's the area of a triangle? Well, it's 1/2 base times height. So the base of this triangle is 2 units, and the height is 2 units. So it'd be 1/2 times 2 times 2, base times height. And then what's the area of a rectangle? Well, that's length times width. And if we look at the width there is 2, and then the height of our rectangle here is also 2. So the area of our rectangle is 2 times 2. And if we do the arithmetic, we get 6. So that's just kind of neat that it agrees with what we, the much more complicated definite integrals that we calculated. Another way to do this, and it works for this one, is to just go through and count how many unit squares that you have inside that region. So, if we're counting, here's a full unit square. Here's one. Here's one. Here's another one. That's 4. Here's a 5th one. So we have 5 squares. And then we have those diagonal half pieces. So this would be like 5.5. And if we combine those together, we would get 6. So there's 6 unit squares inside this region. That's another way to think of it. All right. So what we've seen in this example is how to deal with piecewise functions a bit. But this was a function that was on or above the x-axis. So a lot of the functions that we normally consider, they go above the x-axis, they go below the x-axis, and they go back above. And we want to be able to see what the definite integral means for those cases as well. And that's what we're going to look at next. So we're going to consider 3 separate cases here. So in the first case, we have a region that is on or mostly above the x-axis. And this is what we've been looking at. So what does the definite integral, if this is the function that we're looking at and we're between a and b, what does that definite integral represent? So the integral from a to b of f of x dx, well, we've seen this. This is equal to the area of that shaded region. All right, what happens if we go to that middle example where we have our function f of x, we're in between a and b, and we see that our region is below the x-axis? We can still talk about the definite integral, but what we end up with, still related to area, but because it's below, the definite integral is going to be equal to the negative of the area. And then finally, in that last picture, here we have a function that goes above and below the x-axis. And so let's say we are looking at in between a and b. We could still talk about the definite integral, but the question is, what does that definite integral represent? So here we have a region that is partially above and partially below the x-axis. So the question is, what does the definite integral represent in this case? Well, it's going to still be related to area, but it's going to be the area that sits above the x-axis minus the area that sits below the x-axis. So it's you kind of get some subtraction there. So you're kind of balancing, in a way it kind of tries to balance itself out. And we give this a special name. When we're looking at the area above minus the area below, we call that the net area. So for just any continuous function, f, on the interval a, b, if we calculate the definite integral of f of x from a to b, what we're really calculating then is the net area. How much of the region sits above the x-axis minus how much of the region sits below the x-axis. And so this is what we're calculating in general when we do a definite integral, without the requirement that f is non-negative. So we've kind of gotten rid of that requirement. F can now go above and below the x-axis. And so when we look at its definite integral, we're doing this net area calculation. It's the area of the region above minus the area of the region below. So let's try kind of look at this a little bit more closely. And let's say we wanted to just calculate the total area of that region that sits between the curve and the x-axis. So let's say we want the total area. So we have to, because there's two different regions there, we're going to end up having to kind of split up the integration. So first, there's something we just saw, the net area. This is the definite integral of our function from a to b. So this is our function here. This was a, this was b. And how we calculate the net integral area is just the definite integral, but our interpretation of it is it's the area that sits above the x-axis minus the area that sits below the x-axis. So to calculate the total area, we have to instead integrate not just our function, we have to integrate the absolute value of our function. And so the total area of that shaded region is, we have to calculate the area that sits above the x-axis, and then we have to calculate the area that sits below the x-axis, and we add those two areas together. And so our strategy for calculating the total area is we want to figure out the x values where our function intersects the x-axis. Then we'll determine the intervals where f is above or below the x-axis. And then we're going to calculate the area over each of those intervals. So basically, we're going to calculate the area of each smaller region individually using definite integrals, and then we'll add the results. So we're going to look at this region here, and let me use B because it's below. We'll look at just that region that sits below the x-axis, calculate the area of that region. Area is positive. Then we'll look at this region over here that sits above the x-axis, calculate that area, and then we'll just take the area of those two regions and add them together to get the total area. And one little thing, little note here. We're interested in where our function intersects the x-axis is because that's where our function can go from below to above or above to below the x-axis. And we're seeing an intersection point right here in the middle. So that's where our function intersects the x-axis, and we have a change from being below to being above. And the way we do this is we set our function equal to 0, and then we just solve for x. So let's try an example where we find the total area. So let's look at this function f of x equal to x squared minus x. And we're going to look at this function on the interval from 0 to 2. So for part A here, we're going to find the total area of the region that sits between our curve and the x-axis. And we're going to do this with definite integrals. So first thing we want to do is we want our intersection points. We want to figure out where our function crosses the x-axis. Now we have a graph here, and we can see that it happens at x equals 0 and x equals 1. But if we were doing this without the graph, what we would do is we'd take our function, which is x squared minus x. We would set this equal to 0, and then try to solve it. So factor, quadratic formula, one of those probably. Here, this one factors into x times x minus 1 equal to 0. And then we just set each of those factors equal to 0, and we get x equal to 0 and x equals 1. So that's where we're getting these two intersection points from, algebraically. All right. So we want to find the total area of that shaded region. And what we're going to do is we're going to ultimately break up our integration. So we'll calculate the area for that region that sits in between 0 and 1. And then we'll calculate the area of the region that sits in between 1 and 2. And so to help us with this, we want to identify where our function f of x is above or below the x-axis. And we'll do this with a sign chart. So we're looking at the interval from 0 to 2, and let's plot our intersection points. So we found that we had an intersection point at 0, and then we also had an intersection point at 1. And so this kind of splits up our interval into two subintervals, and we just want to figure out, is our function above or below the x-axis on each of those intervals? And we can just do this by looking at our graph. So in between 0 and 1, we see that our function is below, and in between 1 and 2, we see that our function is above the x-axis. If we didn't have the graph, what we could do instead is just use test numbers. So sort of like what we were doing with our sign charts for increasing, decreasing, and concave up, concave down, same idea. Use test numbers, pick a test number that's inside each of those intervals, plug it in, and see if you get a positive or a negative value. If it's negative, you're below, and if you're positive, you're above. So then we go through and we calculate the area for each individual region. So let's start with the area that's below the x-axis. And so what we're going to do is we're going to integrate our function from 0 to 1. But because our function is below the x-axis on that region, to get the area, we have to put a negative in front. So without that negative, let's get rid of the negative for a second. If we were just going to do that integral, we'd end up with a negative value, and we can't have a negative value for area. It needs to be positive. So because the region sits below the x-axis, we introduce the negative there. Then we also need to find the area for the region that sits above the x-axis. Now this occurs in between x equals 1 and x equals 2. So we're going to integrate from 1 to 2 our function x squared minus x. And because this is above the x-axis, it's just the integral as is. So if we're looking at a region that sits above, you can just think of it, it's just your integral, maybe put a plus sign in front. If it's the region that sits below, well, then we have to introduce a negative in front of the integral. And that's because our function becomes negative when it goes below the x-axis, and it's positive when it sits above the x-axis. And then from here, we just calculate these integrals now. So this one, we're going to have that negative in front. We end up with the antiderivative of 1/3 x cubed minus 1/2 x squared. And then we evaluate from x equals 0 to x equals 1. We evaluate, and we get negative in front, and then negative 1/6 once we evaluate from 0 to 1 there. And that just is 1/6. So that's the area for that little region in between 0 and 1 that sits below the x-axis. Now what about that region that sits above the x-axis? There we're integrating from 1 to 2. And same antiderivative, except without that additional negative in front. So the antiderivative for this one is just 1/3 x cubed minus 1/2 x squared. And we're integrating from x equals 1 to x equals 2. We do our evaluation, and what we end up with is 8/3 minus 2 minus 1/3 minus 1/2. And if we do our simplifying there, we end up with 5/6. So the region for that area for that region above the x-axis is 5/6 units. So then to put it all together, the total area is then the area for the region that sits above minus the area, or plus the area that sits below. So it'd be 5/6 plus 1/6, what we found, which is equal to 1. So the area of that entire shaded region there would be equal to 1 unit. So we have to, for total area where we have a function that's kind of below and above, if we're trying to calculate the total area there, we have to split up our integration wherever our function crosses the x-axis. So this was for total area, just getting the total area for that region. In part B, we're just going to do the net area. So the net area, this one's a little bit more straightforward. So the net area is just the integral of our function over the interval, in this case from 0 to 2. So we don't have to worry about intersection points for net area. So we just integrate our function as is, x squared minus x. Same antiderivative that we saw, 1/3 x cubed minus 1/2 x squared. And we're evaluating from x equals 0 to x equals 2. And if we do the evaluation, top number goes in first. We get 8/3 minus 2. And then plug 0 in, we get 0. So we end up with 8/3 minus 2, which ends up simplifying to just 2/3. So the net area, what the net area is really calculating is, if the net area is positive, you can kind of think of it as it's measuring, where your region falls, where your region sits. So if we have positive net area, more of the region is above the x-axis. If we have negative net area, well then more of your region sits below the x-axis. And it's perfectly possible, perfectly reasonable that we do an integral and we get 0. So what happens if we have a 0 net area? Well, then it's balanced. The same amount of area that sits above the x-axis, we have a similar region, similar sized region that sits below. And so it's a perfectly balanced region that we're looking at. So you can kind of think of it like integration is sort of, and we'll see it in Calc 2, is it's related to center of mass. So, you know, if you think of, you have a pen and you have a balance point in the middle for net, you know, for net area, if, let's say the tip of the pen is the positive direction here, if I have more mass concentrated above the x-axis, my integrals, you know, that's where most of the mass is, so it's going to be kind of lean that way. If I have more mass that is in the negative direction, I'm going to tip that way. But if I have the same amount on either side of the x-axis, it's going to be perfectly balanced. And so sort of an application of a definite integral like this is in center of mass calculations. So when we have a 0 value for our integral, really what it's saying is that the area that sits above the x-axis is exactly equal to the area of our region that sits below the x-axis. So it's balanced. And we can check this out for this problem, because on the last page we figured out what the area for the region that sat above, and we figured out the area that sat below. And so for net area, we subtract those two quantities. So net area is the area of the region that sits above the x-axis minus the area of the region that sits below. And what did we figure out? The area above we said was 5 over 6, and the area below was 1 over 6. So above was 5 over 6, area below was 1 over 6, and what we end up with here is 4 over 6, which is 2/3. So that just kind of confirms what we already calculated here. And we can see, you know, this visually makes sense. When we look at the region here, it looks like we have more of our region that sits above the x-axis than sits below. So this kind of little piece of our region here is sort of canceling out, you could think of it like this, it's canceling out this little piece. And so we're just looking at, you know, what's the area of the difference there. All right. Let's try another one. And we're going to think of it, kind of think of these integrals in terms of area. So that's what we want to do. And sometimes we can get away with just using basic geometry. So for the first one here, we're going to do the integral from 0 to 2 of the square root of 4 minus x squared dx. And square root functions are notoriously difficult to integrate, very challenging to find the antiderivative of, if there's more complicated terms underneath. Square root x, we can do that one. But if there's an x squared under there, much more difficult to do on its own. But we can still figure out what this definite integral is, because we can interpret that square root function kind of in a geometrical sense. So let's take that function and we'll set it equal to y. Y equal to square root 4 minus x squared. And if we try to kind of work with that expression, maybe try to produce something that looks a little bit more what we're used to. Maybe we square both sides, get all the variables on one side. We would end up with the equation x squared plus y squared equal to 4. And that might look a little bit more familiar, that equation. So this is just the equation for a circle of radius r equals 2, centered at the origin. So centered at the point 0, 0. And that's what we're seeing on this graph, is we have part of a circle centered at the origin of radius 2. Now, why is it only half of the circle? Well, because our original function was the positive square root, and that's why we're getting the top half of our circle. If it was the negative square root, then we'd have the bottom half of our circle. All right, so we're trying to do the integral of this function from 0 to 2. So on our x-axis, we're only looking at the region that sits below our curve from 0 to 2. So we're only looking at this portion, and we're trying to find the area of that portion, essentially. So this is the interval from x in between 0 and 2. And we see that it's half of half a circle. So really what we're trying to do with this definite integral is we're trying to figure out the area of 1/4 of a circle. And we have a nice formula for area of a circle. So it's pi r squared. And because we're only looking at 1/4 of it, half of a half, we multiply by 1/4. And so the radius of this circle is 2. So we end up with 1/4 pi times 2 squared, which ends up simplifying to just pi. So we had this complicated definite integral, and we don't know how to do this one yet. So if you tried to do this one, try and use substitution. This is one we can't do. We don't know the technique yet for doing this one. So in terms of getting an antiderivative. So the best we could do for calculating this definite integral at this point is to try and interpret it as a geometric figure. And here we got kind of lucky. It was part of a circle. And we have a nice formula for the circle. So that one, maybe try it out, see what you can work with. But we'll see how to do that, find the antiderivative of that function in Calc 2. So at this point, we can't do the antiderivative for that. All right, what about the next one? We're going to look at the integral from 0 to 3 of x minus 1. And, if we're interested in the graph of our function, we're looking at, let's set it equal to y, and y equals x minus 1. We know what that is. That's a line. And that's what we see in our graph here. It's just a line. It crosses the y-axis at -1, and it has a slope of +1. So we see that in our graph. And we're doing the definite integral from 0 to 3. So really, what we're trying to do is we're going from x equals 0 all the way to x equals 3. And so with a definite integral calculation, we're looking at really the area of this region. And I'll use a different color. Area of this region that sits between our x-axis and our curve. And then we're also looking at the area of this region that sits between our curve and the x-axis. Now, we see that we have kind of two different pieces of our region here. We have this region where it sits above, and then we also have this region where it sits below. And so doing the definite integral here is really calculating the net area which is really the area that sits above the x-axis minus the area that sits below. And so really what we have here is two triangular regions. So the area that sits above the x-axis, that's the larger one here. And area of a triangle is base times height. So we see that the base of this triangle is, or the height of our triangle here is 2, and the base of this triangle is also 2. So we're having an area of, we have a triangle where the base is 2 and the height is 2. And then for that triangular region that sits below the x-axis, we're going to figure out the area for that triangle. And there the base is equal to 1 and the height is equal to 1. They don't have to be the same, but in this case they are. And we're going to subtract those two area calculations. So for our first area there, it's 1/2 base times height, so 2 times 2. For our second triangle, it's going to be 1/2 base times height, so 1 times 1. And doing the arithmetic there, we end up with 3/2. So that's what the value of this definite integral is. Now another way to kind of think of that, it's the net area. So we could kind of go through and just count up how many square units that we see if we have a nice kind of triangular or rectangular region. And so what we're seeing here is we have this section that sits below the x-axis. And we could think of it as sort of canceling off any effect that this similarly shaped little triangular region has. So those just cancel out. One sits below, one sits above, and they just cancel out. And what we're left over with then is that doesn't look good. But we're left over with this sort of trapezoidal region. No, can't even read it anymore. And so what we see there in this leftover region is we have a unit square, which has area 1. And then we have this sort of half of a triangular region, which is half of the square. So adding those two together, we get 1.5. And that's really what the net area is doing, is it's saying, all right, let's take how much of our region sits below the x-axis, cancel that off with some of the region that sits above, and then we're looking at what the difference is, how much is left over. And so in this case, what we have left over is 1.5 units, square units. All right. So fun with areas. And it turns out really area is the right context. So when we're thinking about definite integrals, we want to have in the back of our heads areas. It's going to make a lot of the properties and little tricks and techniques just make more sense if we have area in the back of our mind. And so we've seen a lot of properties of definite integrals. And we've kind of used them in calculations. But now we're just going to reframe them in terms of area under the curve. So the first one that we've seen is when the limits of integration are the same. So we're integrating a function from a to a. So the upper limit is equal to the lower limit. And turns out that that definite integral is equal to 0. And really, the limits of integration really tell us about the width of our interval. And so what we're seeing with this property is that we're really looking at a kind of a region, a rectangular region even, with 0 width. So we're really looking at this definite integral over the interval from a to a, and that's an interval with 0 width. So when we try to calculate the area of a rectangle with 0 width, well, area of a rectangular region is length times width, and if our width is 0, then the area should be 0. And that's what this property really says. So if our limits of integration are the same, really we're looking at a region with 0 width, and so the area of any region with 0 width should be 0. We also had this property that let us split up the integration over different subintervals. And really this makes sense in the context of area as well. So let's say we were given a graph of some function f of x, and we were interested in calculating the area under the curve from a to m. So maybe this is a and this is m. Forgot how to write an m there. So that's, if we're interested in looking at the area under the curve from a to m, and then we're interested in the area from m to b, well, we could just save ourselves the step and look at the area just going all the way from a to b. So the integral of f of x from a to m, that's really calculating the area from a to m. Then the integral of f of x from m to b is calculating the area from m to b. And what this property says is that we could look at the area of the left piece, look at the area of the right piece, and just add them together, and we get the area, we get the total area. We get the area from a to b. So another way to think of this is it's the area on the right piece plus the left piece plus the area of our right piece, and it just gives us the total area here for this positive function, non-negative function. So you can just kind of split up your region into little pieces, just calculate the area of each of those little pieces, and then just add the areas together. So something that, seems pretty plausible. So a lot of these definite integral properties kind of make sense if we think of them in terms of area. Now finally, we're going to look at what happens when we have symmetric functions, and also going to be helpful to think of this in terms of area. So we have two properties here. One that tells us what happens if we try to integrate an even function, and the other one if we integrate an odd function. And we'll see what the specific definition for an even function and an odd function is in a second. But let's suppose that we have a function f that's continuous on the closed interval from negative a to positive a. So that's important. That's what our interval has to be. It has to be from negative a to positive a. If it's different, then these properties don't directly apply. So we need sort of this sort of balanced interval, negative a to positive a. If our function is even, then the integral of our function f from negative a to positive a, we can kind of simplify it a little bit. And it's equal to 2 times the integral from 0 to a. And we'll see why kind of in a second why this works out. For an odd function, if our function is odd, and we integrate our function from negative a to positive a, well then we get 0. So this is the one that's really handy, is if we know our function's odd, we don't even have to worry about finding an antiderivative. We can just say the definite integral is equal to 0. So let's look at what happens, some examples of what an even function might look like and what an odd function might look like. And we notice that they're symmetric. So an even function just looks like a mirror image across the y-axis. And so probably one of the more common functions that we see that is an even function is, and this is what we have graphed here, is cosine x. So cosine is an even function. It's symmetric about the y-axis. And so let's look at that first property. If our function is even and we want it to integrate from, let's say, negative a to positive a, well, because this region is symmetric about the y-axis, these two kind of smaller regions have the same area. So the region for the piece that sits on the left here has the same area for the piece that sits on the right. So this area and this region, these two regions have the same area. So if we were doing the integral, really what we're calculating is the area under the curve, and it's equal to the area for the left piece plus the area of the right piece. And since they're equal, it's equal to 2. We could just multiply, we could just double the area for that right region. So we could just instead calculate the area for that right piece that sits to the right of the y-axis, and then just multiply the result by 2. And what is the interval for this right section? It's between x between 0 and a. So just looking at that right section of our region there, that's what we're seeing with integrating from 0 to a here. We're just calculating the area for that right piece, and since the right piece and the left piece have the same area, we just double it up. Now for an odd function, we're going to see sort of the opposite happens. And so one of our more common odd functions that we encounter is sine. So sine is an odd function. And that's what we have graphed here. This is our sine function. And so if we were trying to integrate the sine function from negative a to positive a, what we'd see is that we have two regions with the same area. So we run into the same kind of idea here. This odd functions are symmetric, but they're symmetric through the origin. So they kind of look like a reflection through the origin. But now what the region that sits above the x-axis is on the other side of the y-axis is now below. So these two regions that we have here have the same area, but one of the regions is above and one of them is below. So the net area, which is what we're doing with a definite integral, where it goes above and below the x-axis, the net area is equal to the area that sits above minus the area that sits below. But because those two regions have the same area, the graph is symmetric, they end up canceling out. So the area above is equal to the area below, and we get 0. So these are just some neat properties that occasionally help us out if we have, a more complicated integration problem. But the key requirement here is that our interval needs to have it needs to be balanced like this. So in order to have the regions have the same area, we need to go from negative a to positive a. All right, so let's see what it actually means to be an even function or an odd function algebraically. So for something to be an even function, if we were to take negative x and plug it in, we end up with just f of x. So we end up with the same result as if we were to just plug in positive x. So an even function, we take negative x, we plug it in, and somehow the negatives sort of get canceled out in our work. And so, where do we come up with this odd and even kind of terminology? Well, power functions. So if our power function has an even exponent, it's an even function. So it's symmetric about the y-axis. If our function has an odd exponent, well then it's going to be an odd function. So let's show that based off this definition, let's show that our function, this function f of x equal to x to the power 6 plus 1 has an even exponent, so we're kind of thinking it's going to be an even function. But let's show that it's an even function. So what we're going to do is we're going to take negative x and we're going to plug it in to this function. So wherever I see an x in my original formula, I'm going to change that to a negative x. So I'll have negative x to the power 6 and then plus 1. And then we try to simplify. And with an even function, all of those negatives that we introduce should end up getting canceled out. And that's what we see here. We could think of that. Really, we could think of this negative x as negative 1 times x, and then we distribute the exponent. So we get negative 1 to the power 6 times x to the power 6 plus 1, and then negative 1 raised to an even power is positive 1. So we just get x to the 6 plus 1, and this is exactly what our original function is. So this is exactly f of x. So that's an even function. And so all even functions, if you were to graph them, it would be like a mirror image. The right side of the graph and the left side of the graph would be a mirror image of each other. Now for an odd function, what happens with an odd function is when we plug in negative x, what happens is some of the negatives live on, and we ultimately end up with negative f of x. So the definition for an odd function is f of negative x is equal to negative f of x. So you can almost think of it like you're bringing the negative out. Normally we can't do that. We can't bring numbers outside of our function notation like that. So this is something special. And we're going to show that this function tan x over 1 plus x squared plus x to the fourth, we're going to show that this is an odd function. And the way we do that is by plugging negative x in. So wherever we see an x, we're going to change that to a negative x. So we end up with tan of negative x over 1 plus negative x squared plus negative x to the fourth. Now let's work with that tan function a little bit. So on the last page, we said that sine and cosine, sine was an odd function, cosine was an even function. So let's relate tan into sine and cosine. So tan of negative x would be equal to sine of negative x over cosine of negative x. Sine is an odd function, so we can bring what happens then is the negative comes in front. And cosine is an even function, so the negative just kind of disappears with the even function, and we just end up with cosine x. Just based off of our definition. So since cosine is an even function, cosine of negative x is equal to cosine of x. And this is just equal to, let's put the negative in front. So take the negative off of the sine, and we end up with negative sine over cosine. So this is equal to just negative tan x. So we see that tan is actually an odd function. So tan on its own is an odd function. So let's fill that in. We get negative tan x on the top, and then we know with those even exponents, those just cancel off the negative, so we end up with 1 plus negative x raised to the power 2 just simplifies to x squared, and then negative x to the power 4 just simplifies to x to the 4, so the negatives just get canceled out by those even powers. And then, finally we end up, let's put the negative in front. So we get negative tan x over 1 plus x squared plus x to the fourth. And that whole thing inside the parentheses here, that's our original function. So we have that negative in front. So we end up there with negative our original function f of x. So for this particular function, when we plug negative x into it, the negative kind of ends up in front ultimately. So we end up with negative f of x. Something very special. That doesn't happen always. So we see that this is an odd function. All right, so let's use that in our integration. So let's use that symmetry to help us with these definite integrals. So let's start with the first one. We're going from negative 2 to positive 2 of x raised to the power 6 plus 1. We showed that that was an even function. And because our limits of integration are symmetric, that's the other thing we need to check. we're going from -2 to +2, what we can use is that symmetry property that says this then is equal to just double up the integral, but then we shorten our interval. So we're going to double the integral from 0 to 2 of our even function. And now it's just regular integration. So find the antiderivative, keep the 2 in front. Basic power rule, antiderivative of x to the 6 is 1 over 7 x to the 7. Antiderivative of the +1 is x. And then we evaluate from x equals 0 to x equals 2. Plug in, and we end up with 1 over 7 times 2 to the power 7 plus 2, and then we multiply by that constant 2 in front that we got from doubling it because we had an even function. And then we would plug 0 in, but we don't get any contribution from 0. So we'll still, kind of go through the motions here. Say we plugged in 0, but we end up with 0 for that part. And so really why we would use this is it's always nice to plug in 0. Usually it's nice. So the benefit of using this, we can't always do it, but the benefit is 0 is usually a nice number for evaluating. So a lot of times when we plug in 0, it makes things a lot easier to evaluate. So, much easier than, say, if we were to just plug in -2. So that's why we might use this. This is just to make the evaluation just a little bit easier for us. Now for the last one, doing the integral from -1 to +1, and this is our function tan x over 1 plus x squared plus x to the 4th. And we saw that this was an odd function. And, if we kind of split this function apart, we went through the kind of the calculation side of it to show that it was an odd function. But if we kind of split this apart into 1 over 1 plus x squared plus x to the 4th, everything is even powers here. So this is an even function. And then we said that tan was an odd function. And so if you have an even times an odd function, the result is an odd function. So it kind of works like when you're doing, positive times a negative, the result is negative. Well, even times an odd is odd. If we had 2 even functions that were multiplying, we would end up with an even. Or if we had 2 odd functions that were multiplying, we would end up with an even. So it kind of has that, 2 odd functions would be similar to like a double negative where you get a positive. So that's just another way to think of these even and odd functions. In any case, we already showed that tan x over 1 plus x squared plus x to the 4th is odd. And then we also note that we have the symmetric limits of integration here. So we're going from 1 to -1. So that's just also important to note. And it's an odd function. We have symmetric limits like that. Equal to 0. We're done. No antiderivative needed. So odd function, that property really simplifies things down. And, looking at it, that function, that would be a pretty complicated function to try and get the antiderivative of. So at this point, we don't know how to do that one either. So if you're kind of looking at something and, you're kind of stumped on it and you happen to notice that the limits of integration are symmetric, well, maybe you can get lucky and see that it's an odd function and the integration just becomes 0. All right, so that's just kind of looking at definite integrals in terms of area. So we were able to kind of think of these other properties of definite integrals and kind of help to frame them in the context of area. Let's see. About 5 minutes. I think we'll stop for today. Yeah, we'll stop for today. So again, just a reminder, we'll get to learning outcome IC3 on next week. So we'll see how definite integrals relate to velocity and distance and displacement. And then after that, we're going to see the actual definition of the definite integral and really see why it allows us to calculate area and ultimately allows us to calculate distance. So we'll look at the actual definition, probably start that next time. But in any case, we'll stop there for today. Just one last reminder so if you have recitation today, you're doing exam 6. Next week, Thursday at 6:30, we have our last follow-up exam, which covers all the material from exams 1 through 6. So it's, again, next Thursday, 6:30 to 7:30, 1 hour long. Make sure you just double check your schedule. If you can't make it at that time, please send me an email by tomorrow, just kind of explaining why you can't make it, and send me a screenshot of your class schedule from your Hub Student Center, just so I can see what the conflict is. All right. Have a good weekend, and we'll see everyone next week. And if you're taking the exam, I'll see you today.